The next section of the textbook is neutralization reactions. Before we start neutralization reactions, we're going to start with the acid-base indicator, which is basically just a dye that distinguishes between acidic and basic solutions. So litmus paper is either pink or blue, and so it just simply tells you whether something is acidic or something is basic. Then they get much more progressive. This is what they call a universal indicator, and a universal indicator, you can see that in the low parts, 1 and 2, those look pretty identical, and the higher parts of 10, 11, 12 look pretty identical, but between 9 and 3, then you can see to some extent what the pH is. And so this is a pretty advanced indicator that changes a lot of different colors. Most indicators are just 2 colors. Acids and bases have 2 definitions that we're going to study this semester, and a third one we're going to study next semester. And this goes back to the oldest definition of an acid is anything that has H plus when it's dissolved in water. So here's an image of hydrochloric acid with that H. A base is a substance that produces hydroxide when it's dissolved in water. So this is sodium hydroxide, and here's the OH that comes off in solution. As time progressed, they realized that acids still had the hydrogen, okay, and H plus is the same thing as a proton. Base, however, expanded its definition. It no longer had to have the hydroxide, but it was something that accepts the proton or the H plus into another species. So here I have nitric acid, which is the acid, donating the hydrogen to water, and so it forms hydronium ion concentration and leaves behind the nitrate. The base is, or in this example, the water is now my acid. It's going to donate its hydrogen plus, or a proton, to NH3. Okay, there's a lone pair of electrons here, and it becomes NH4 and then leaves hydroxide. So this is kind of confusing because you'll hear different terms in different classes. H plus is a lot of times called a proton. So this would be the same thing as a proton, because hydrogen as an atom or element has 1 proton, 0 neutrons, and 1 electron. This goes all the way back to chapter 2. And so when I lose the 1 electron to become H plus, it has 1 proton, 0 neutrons, and 0 electrons. And so a proton and an H plus mean the same thing. And when I react with water, it forms H3O plus, and this is called hydronium ion. And so basically what this means is that H plus is the same thing or equal to the hydronium ion, which is also called a proton. So there's 3 different names for what we can call the same thing: a proton, an H plus, or hydronium ion. In biology, they tend to use the term H plus, and in chemistry, we tend to use the term hydronium, because H plus is typically going to always be accepted by this water molecule. Next is a strong acid versus a weak acid. This goes back to the last section with electrolytes, and strong electrolyte and weak electrolyte. It means basically the same thing, that a strong acid completely ionizes in water, and a weak ion only partially ions in water. So what I have here is a figure that shows a strong acid, and you see the fact that none of these are together, versus a weak acid. I still have my H plus and my A minus, but I have some that stay together as a conjugate there, okay, or as the reactant itself, okay. So this has nothing to do with reactivity. This has to do with simply how it performs in water. So strong acids, which you'll see on the next slide, are things like hydrochloric acid, hydrobromic acid. To me, the worst weak acid is HF, or hydrofluoric acid. Hydrofluoric acid is the one acid that I won't touch. And the reason I won't touch it is because when you get it on your skin, unlike most of the acids that we deal with that are classified as being strong acids, as long as you have small concentrations and small interactions, or it's only on your hands for a period of time, it doesn't do damage to the skin. Hydrofluoric acid you cannot just rinse it off. It starts reacting with the skin so quickly that you have to go to the hospital and actually get a shot of it. It's the only acid that will actually dissolve glass also. So again, the reactivity of the acid doesn't have to do with the strength of it. The strength is just what happens when you put it into water. A strong base is simply a base that completely ionizes, okay, so it forms a hydroxide, and a weak base only partially ionizes. So same basic definition, it's just for a base. There are 6 strong acids, and there are 6 strong bases. The strong acids to me are the hardest to learn. These 3 are grouped. This is all group 7A on the periodic table, or 17, depending on which system you use. And you'll notice that hydrofluoric acid being the top of that column isn't included. Then you have, this is perchloric acid, sulfuric acid, and nitric acid. And so there's really no grouping of these 3 on the periodic table. So you have to more or less memorize these. The bases are easier because on the periodic table, they are grouped on the periodic table. So you go lithium, sodium, potassium, and then you go over one row and you have, this is calcium, and then strontium and barium. So this is lithium to potassium. This is calcium to barium. So they make this little jig on the periodic table. And these are in group 2A, so they have 2 hydroxides. Again, though, you need to know and recognize these. And why that is in this next slide. So it asks the question to identify each as a strong or weak acid or base. So the first thing we need to do is identify if they are an acid or a base. In chapter 2, we identified acids because that was one of our nomenclature schemes. And how do we do that? It starts with an H. And a base does not. So if I look at this first one, NH3, there's no hydrogen first, so this is a base. The next question is it one of the 6 strong bases? Well, all the 6 strong bases, you know, had hydroxides to them. So therefore, if it's not strong, the only alternative then would be to be a weak base. This one starts with a hydrogen, so therefore it's an acid. Is CNO one of the strong acids? No. So therefore this is a weak acid. So it's simply, is it on that list or is it not on that list? I suggest you stop here and pause it and see if you can go back and do the next 2 on your own. This one does not start with a H, so therefore this is a base. Magnesium is not one of the 6, so therefore it is a weak base. That's a really odd, terrible B base. This one starts with a hydrogen, so therefore it's an acid. This one you have to be real careful. HClO4, or perchloric acid, is a strong acid, but HClO3, which is chloric acid, is a weak acid. So it has to match exactly. And we will pick up, there's more in this section, we will pick up with that on the next video.